So the example is a simple parallel plate capacitor. So we have one electrode that's grounded, one electrode with 10 volt, and it will be modeled in 3D despite this rotational symmetry, we could assume. We will use a quarter model to use a little bit of symmetry at least. And we have air or polyimide between the electrodes. So these are the two options that are given in the template files. And the aim is to compute the capacitance of this specimen. And we can use this model to study the influence of the stray field, which is not considered if you simply take the analytical solution that is typically simply disregarding this stray field. Okay, so what is the analytical estimation? If we have parallel electrodes and symmetry, these are circular electrodes, so we can compute the electric field simply by the potentials and the distance between the electrodes. So this is the electric field strength. And then we can compute the energy stored in the capacitor given by this relation, 1/2 C times V squared, where V is our voltage. And we can also obtain the energy density by the total energy over the volume of our capacitor, which is simply radius squared times pi times d. Okay, so there's another sketch of this example. We consider it's rotationally symmetric. We have dielectric or air between the capacitor plates. We have air outside. We'll specify a natural boundary conditions. And this radius here can actually be increased to study the influence of the stray field. So there are a few questions given here. What changes when you change the dielectric properties of the medium? So for example, polyimide versus air, and how much must be the far field modeled to actually obtain an accurate result. So here we are in the virtual machine in our example folder. Let's list the contents. We have, as usual, a README file, a capacitor.xml input file, a met.xml input file, and a Trelis journal file, and a run file, which should do the meshing and compute the problem. So let's look at the geometry in Trelis first. So I'll open the journal editor, and here I'll open the capacitor journal file. Get this side by side so you can see both things at the same time. So you can see that we have a few journal commands here. With reset, we simply reset everything. This is relevant if we run journal files more often than once, so we always have a clear start. And then Trelis allows you to define variables here in this manner. You start with the hash and then the curly braces defining the variable r equals 3.3 to the power of -3, so 3 millimeters for the radius of the capacitor, and the capital R is the outer radius, and then we'll simply create the cylinder. I'll just run this partly. So I'll choose place selected. So we see here we have the cylinder of our capacitor. We will have a top surface and a bottom surface at the end. And the next thing is we create a sphere around the capacitor. So again, I can just paste it also into the command window. If we zoom out, we see, okay, here's the sphere around the capacitor. What we now want to do is actually to do some boolean operations, and you can find those here at the modeling plane. Perform boolean operations, and then you can define boolean operations on bodies. And what we want to do is we want to subtract body 1 from body 2 and keep both things. So you can either do this via the GUI or via the journal file. This is already given. Typically, the workflow is you start by clicking in the GUI, and you actually monitor your history window and see what comes out. So I'll just illustrate this here with the first subtraction command. So we see the operation subtract. Trelis shows us what will be done. So from our first from our sphere, we want to subtract the inner volume. So I'll select it here in the model tree. So it should be volume 1. Can also insert it here, and we'll select keep original, click apply, and now we should have actually, if we change the view, we can have a subtraction here inside. So we'll have volume 3 and volume 2 was deleted. The important part when we do 3D modeling in Trelis is actually that when we later mesh the structure, we actually need a conforming mesh. That means that the nodes are actually adjacent to each other on both sides. So let's continue with the Boolean operations. We can also cut bodies. This is here in the modify tab. So now this is the imprint and merge already, sorry. Transform geometry. No, it's not intersect. Yeah, as you see, I'm not using Trelis so frequently to find all the things in the GUI, since I usually use the scripting. So decompose geometry, yeah, that looks better. So we can decompose our geometry. I think it is general plane. So for example, we wanted to slice this into the quarter model. So we want to actually slice all volume IDs with the plane, and here we can, for example, use the X plane. And hit apply. So we have cut it via the X plane, and we will also do this via the Y plane because the Z plane is our thickness direction. So let's modify this to the Y plane, also click apply. And we have another quarter. And now we can delete a lot of bodies. So we can use the delete and select here with control. We can select. No, I can't do anything with control because I'm in the virtual machine. So I have to do this in sequence. Okay, so this is the geometry using the symmetries we actually want to end up with. Just to look at the model tree here, we can select everything down to surfaces. So let's see a surface that is actually should be contained in both bodies, which should be surface 32. This is the surface of volume 6. Volume 6 is our capacitor. So the top surface is surface 32. And let's see on volume 7, we actually have the adjacent surface. Let's go through them. This is surface 47. So you see Trelis actually has distinct surfaces for these bodies. So if we simply try the meshing now, let's see what happens if we simply do a volume mesh. So let's select the meshing discretization here. Click mesh. It doesn't want to mesh. Yeah. So let's switch the meshing scheme to, for example, tetrahedrons. So the TED mesh should actually always work. Let's see if this is true. TED mesh works. We get the mesh, but of course it's tetrahedrons. We know that the quality of tetrahedrons is not that high. So let's see how we can mesh this body. We have selected automatic sizing. We click mesh. It meshes with the hexahedron algorithm, and what you clearly see here, we don't have coinciding nodes here at the two distinct surfaces, which is of course a problem if we do not use non-conforming interfaces or any special techniques to handle that. So what we typically do have to do in Trelis is the so-called imprint and merge command, which is a geometry command. Imprint and merge geometry. We have to actually tell Trelis to imprint and merge all volumes. And if we do this, let's see what happens. What happens internally is that Trelis should project the surfaces on top of each other and then actually merge the adjacent surfaces together. Apparently the operation didn't work, maybe because it was meshed already. Let's try imprint first. Imprint this one with the outer one. Actually, the imprint and merge in 3D should actually do the trick. Maybe I have to select them 6 and 7. 6 and 7, apply. We have all of the mesh. Okay, so apparently this is the typical demonstration thing. Let's start over. I have the script here anyway. Run selected, play selected. So we'll start over. I did another Boolean operation here, which is the web cut to actually split this outer region in two regions, because this enables Trelis to use a nicer meshing scheme for the outer surface here, because this front surface can be actually swept to the back surface. So Trelis can do a 2D hexahedron mesh on the front and sweep it around the angle to the back. And this gives usually a very nice hexahedral mesh. If we now do imprint and merge, we can again look here, imprint volume all, apply, and then we should actually have already the made. Now we don't have the matching surfaces yet, only if we do the merge volumes all. And what happens now is that if we have here now an adjacent surface, let's look first, this is volume 1 and volume 3. So they should have an adjacent surface. Let's go through them. This should be 28, and you can see both in volume 1 we have surface 28, and in volume 3 we have surface 28. So this ensures that we actually get a conforming mesh between the domains. So finally, these were the two imprint commands, and then we can do the meshing here again via the terminal. You can say play selected, and you see Trelis meshes the model, and you can recognize the sweep mesh here in the purple area. Outside, this is a 2D mesh. This is swept along the radius, and also the other bodies are extrudable in the Z direction, so Trelis can also do a very nice hexahedral mesh on them. So the trick is sometimes in Trelis to split the geometry such that you get a good shape, which is extrudable usually, that gives you a nice hexahedral mesh. Okay, so much. Here we have the input XML for our electrostatic simulation. There's actually not too much new here, except of the PDE definition, which is called electrostatic. We have two regions to consider here in our region list, and we have the boundary conditions, ground at the bottom surface, potential of 10 volt at the top surface. And we define a lot of output quantities, both field results and region results, surface region results, which can be written, for example, here, the electric charge in the text output. Be careful when you define text output IDs. They have to actually be defined in the output section here in the file formats at the top of the XML file. Okay, that was actually all I wanted to show with the XML scheme. Run command, so CFS capacitor should run our simulation. It ran in 1 second. So our state file postprocessing VSM, click OK, use the file name from the state, and let's see if it works. It's loading the state file. Takes a little bit because I've defined a few visualizations already that I wanted to show. First, the capacitor looks like this. Let's look at the elements here. So we recognize our mesh. We recognize our electric potential with the boundary conditions we've set at the infinitely thin conducting electrodes. And the next thing we do is we define a slice plane. So this is actually a diagonal. You can define the direction of the plane by specifying the normal vector. And then on top of the slice plane, we have defined a glyph filter to show the vector field of the electric field intensity. The magnitude is shown as a color, and the direction can be recognized by the direction of the vectors. If we now want to actually use the direction of some vector field to compute streamlines, we can do this with the so-called stream tracer filter. And if I visualize it here, we can see what comes out. The stream tracer requires a vector valued input to integrate over the vector field. You can specify which direction should be integrated, and you should have to specify a line source of points from which the integration is started. So here is the line source definition by simply specifying 2 points. And you get nice streamlines. If they're a little bit thin, you can also use a special filter, which is called tubes, So you say filter and search. You take the tube filter on top of the stream tracer, click apply, let's see what happens. And you have a bit thicker, let's put them on solid color. Stream tubes. This is maybe a bit thick, so you can actually also change the radius here. Let's put a factor of 1/2, and they look thinner now. So if the lines are too thin for you, use the tube filter.